Hello everybody. Today we will be talking about rolling motion. We already know the translational motion where a system moves on a straight line, right? We are using F is equal to ma to find the equations of motion for a system like that. And then we studied rotation. Okay, we defined torque, we defined a moment of inertia. Okay, and we wrote down torque is equal to moment of inertia times the angular acceleration. Torque is equal to I times alpha. And that was Newton's second law for rotation. And the rotation was occurring with respect to an axis passing through a fixed point, right? So we always define a pivot point. In this case, rolling motion, here's the good news. It's the combination of these two. So if you know how to deal with translation and rotation, you will have no problem solving problems in rolling motion. This is good news. Okay, so where do we see rolling motion? Let's suppose you're in a bowling place, you're playing bowling. As soon as you throw the ball, you see the ball move forward. Right? The ball moves forward. At the same time, you feel like it's rotating, right? So it's the combination of rotation. So what the bowling ball does is a combination of rotation and translation. Here's another example. You're in the car, you want to drive, right? Step on the gas and the car moves forward, right? At the same time, the tires of the car actually also rotate about their center of mass. So the tires is going under a rolling motion. They rotate about their center of mass, but their center of mass is also moving forward. So if we call this point our center of mass, what happens in the rolling motion is the center of mass moves forward, right? This is the translation. But at the same time, the whole object, the rigid body, rotates about the center of mass. In short, rolling motion is nothing but the composition of pure rotation about the center of mass. We sometimes call it the spin motion, plus the translation, where all points on this rigid body move forward with the same center of mass velocity. Okay? This is good. So if I pick points on this object, let's suppose I have A, B, C, and D. They're at the rim of this rotating object. If this system was only rotating, what would be the velocities at these points? So at point A, I'll have a tangential velocity pointing this way. At point B, I'll have it like that, point C like that, and point D like that. And from the rotation chapter, what we know is if this radius is r, the tangential speed will have the magnitude r times omega. Okay, this tangential speed is related to this omega. This is pure rotation. And we already showed that all these points, A, B, C, and D, they're also moving forward with the same center of mass velocity. And that's only the translation part. So we call it translation. Since the rolling motion is the combination of these two motions, when you combine these two, what we see is at point A, I will have speed, or the velocity at point A will be just the combination of these two, or the addition of these two vectors. At point B, okay, this tangential velocity is pointing down, V center of mass is to the right. So at point B, I'll have the velocity vector like that. And at point D, it's going to be like this. Point C is critical. Point C is sometimes called point of contact because this point on the object is in contact with the floor. So at point C, the velocity would be v center of mass minus v tangential. Why minus? Because v tangential is pointing in the opposite direction, and I'm picking this direction to be my positive x. Okay, so now we have three cases. First case. Okay. As in the bowling ball problem, sometimes, occasionally, I feel like as soon as I throw the ball rotates less than it moves forward, right? So in other words, it moves a lot, but it rotates less. This is interesting. So in some cases then, the rotation is not as strong as the translation, okay? Or in other words, the rotation is slower than translation. How can we quantify that? Mathematically speaking, r times omega is less than the center of mass speed order. The translation is faster than the rotation. These type of motions are called like skidding. Translation is faster. Second case, okay, we are in our car, the tires are rotating, right? The tires of the car rotating, but the road is slippery. So the friction is really, really small. It slips, right? So as soon as I push on the gas, the tires start to rotate, and they rotate fast, really fast, fast. But the car doesn't move much, right? It doesn't go forward. Oh, the spinning is almost at its own place happening, right? Then you can say r times omega, rotation is faster than the translation. R times omega is larger than v center of mass. And this type of motion is called slipping. Okay? And there is the third case. R times omega is of course equal to v center of mass. This is the third case. And this is called rolling motion without slipping or skidding. If this is the condition, or if this is the case in our system, what happens is the rotation and the translation are somehow connected, right? So we will discuss this connection in a bit, but first of all, let's look at the velocity vectors at these points, A, B, C, and D. Okay. So at point A, if this is rolling without slipping or skidding, V center of mass is going to be equal to V tangential, which is R times omega. So basically, I can write here 2 V center of mass. So here we are assuming this condition. Rolling without slipping. And point B will have speed V center of mass times square root 2. And this would be the same V center of mass square root 2. What happens to point C? Okay. Point C will be 0, right? So the point of contact is going to be at rest at all times if it's a rolling motion without slipping or skidding. Point of contact is at rest. Okay? This is a really interesting property. In some cases we can think of this rolling motion as a pure rotation about this point C. Okay? Since this point C is now a fixed point, the motion of this object can be thought of as pure rotation about this point C. Okay? And this is going to be clear in a bit. Okay, let's move on. Okay, so now we will look at the rolling motion without slipping or skidding case in a little bit more detailed way. As we saw earlier, so that the point A will have this velocity, point C is going to be at rest, right? 0. And the middle point here, the center of mass, will have some speed v center of mass, because this point is not rotating, right? It's just moving forward on a line. So it will have the velocity v center of mass. Okay, and this is my floor. So what we see here, so this looks like as if this point is moving on a circle like that at this given instant of time, of course, and point A is moving on a larger circular arc. So that's why we can actually think of this motion as pure rotation about this fixed point C. Okay? We will see it in an equation actually. So let's write down the kinetic energy of a rolling system. Okay? As we discussed before, there is pure rotation and there is translation. So we will have two terms. You can simply write 1/2 I center of mass omega square for rotation plus 1/2 m v center of mass square for the translation. So this expression is generic, right? It is true for any rolling motion. Okay, speaking of rolling without slipping or skidding, we actually require that the rotation is connected to the translation through this relation. V center of mass is equal to R times omega. So when we plug in over there, so kinetic energy becomes, well, we can write kinetic energy in terms of V center of mass or omega, the way you like it. I'm going to write both of them. First, let's substitute V center of mass in the equation over there. So it will be I center of mass times mr square omega square. You see, this is like pure rotation. But what is this term here? This is nothing but the moment of inertia with respect to point C. Parallel axis theorem, right? This really looks like pure rotation then. So that's where actually see that claim works. Okay, so the kinetic energy can be also written in terms of V center of mass. So if you want to follow that approach, so 1/2, okay, m plus I center of mass r over r squared, that's V center of mass squared. So depending on the problem, you can actually choose either one of these expressions to write down the kinetic energy of the problem. Okay, so now we will move on and we are going to see a little bit more mathematical details about the rolling motion without slipping. Okay, so now I want to do something a little bit more mathematical. Actually, it's still physical, but I'm going to use a little bit more like differential calculus. So let's suppose while this object rolls, okay, the point P moves from here to here. So at some given time t, there is a point P, which is point of contact, and it moves, right? In a given time delta t. Delta t is small, let's say. So the angular displacement here would be delta theta. And the distance it travels is, let's say, delta x. Okay? So the question is, what is the distance traveled by P on the rim, right? This is going to be the arc length. So as this object rolls, right, the point P moves from here to here. So this is the arc length that it travels. So if I look at the pure rotation, so it's simply r times delta theta. Okay? So here comes the condition for rolling motion without slipping. So we require that the distance traveled by P to be the same as the distance traveled on the straight line, the horizontal direction. So if this is the case, we will have rolling without slipping. If we think this as a constant speed motion, let's suppose omega is constant and V center of mass is constant, this is equivalent to saying like if you make one full rotation, Okay, the distance traveled would be 2 pi r. So when you make one full revolution, you travel a distance of 2 pi r, right? Okay, so this is equivalent to saying that. So instead of theta, delta theta, you would have 2 pi, right? But here we do not assume that it's constant omega or constant v center of mass. So if you are looking at average quantities, we will have delta theta over delta t is equal to delta x over delta t. In the limit, as you may all know, delta t goes to 0. Now these become instantaneous quantities. So that's why r times omega is equal to v center of mass. So here's also another way of showing that if there is rolling motion without slipping, r times omega must be equal to v center of mass. This is the condition. Since omega and v center of mass may not be constant, you can simply take the second, one more derivative actually. So this gives you r times alpha is equal to a center of mass. Okay? So when we write down our F is equal to ma equation and torque is equal to I alpha equations, we get A and alpha. And through this relation, we can actually make them related. Okay? So we will have another equation in solving our problems. Okay, so I will discuss one more step and then we will finish. Now we will discuss something really crucial. We are still looking at the rolling motion without slipping or skidding case. So as we showed before, the point of contact in this type of motion is always at rest. And point A has a double speed of the center of mass speed. Okay, since this point is in contact with the floor, we can always think of friction. So there is friction. So if there is friction, this friction has to be static. Why? Static friction. Because the point of contact is not in motion with respect to the floor. So these two surfaces are not moving with respect to each other. So this friction force has to be static. So what should be its direction? Well, depending on the problem, it may be to the right or to the left. Okay? So we will show problems later on and I'll show you different cases. Let's assume for a given problem, static friction is to the right. Okay? It may be 0, but it may be to the right, it may be to the left. Let's suppose it's pointing to the right for a given problem. So what is the power delivered to the system by this friction force? By definition of power, it will be equal to the dot product of F with the velocity of the point of contact, EC. Since this point is not moving at all, this is simply equal to 0. Wow, this actually helps us conclude that the work done by static friction force is always equal to 0. Okay, it does no work. So in problems where there are no other external forces, we can always use the conservation of energy. So this completes today's lesson. In the following videos, I'll be solving problems on rolling motion. I look forward to seeing you soon. Take care, guys. Bye.